Let's start the stream. Oh, I cannot do sound check myself, I guess, since I haven't hooked up Bluetooth. Can somebody let me know in chat if the sound works? If like the volume is fine, etc., and if the video works as well. Assuming. Let me check if. Assuming. Okay. All right. Hello, everyone. Welcome to the Vulkan stream, where we write a Vulkan renderer mostly from scratch. We are using a bit of a different setup today because I got a desktop, I assembled a desktop, it worked. Not from the first try, but I didn't fry any components, which is nice. I do have an ability still to do drawing, like I used to draw on my Surface Pro. I still draw on my Surface Pro. I set up some live sync thingy. This is like Microsoft Whiteboard, so today we will draw a mesh. Yeah, and I also have OneNote working. But today we will try to work in a bit of a different pace, where spend a bit less time sort of explaining things separately from writing code, and spend a bit more time writing code and sort of talking as we write it. The plan for today is to render a mesh. So right now we're rendering a triangle. We want to render something a bit more complex. And we might do this, assuming things work out. I want to do this in a way that isn't really how you normally use Vulkan, how tutorials recommend you to use Vulkan to draw like geometry, right? But feels to me like the correct way to do things long term. I talked before about how, like Vulkan is a complex API. I wish it were simpler. I have a certain idea of how things should work, and part of this stream today is sort of that, right? So yeah, without further ado, let's just draw a mesh. But, well, I guess we can do it without further ado, because first we have to run our program. So this is a different computer with an NVIDIA graphics card. And I ran this code yesterday. Turns out this code does not work on an NVIDIA graphics card. So we have to first fix that. What? Interesting. So Visual Studio tells you it's like to-do comment highlighting, I guess. So if you run our code, then we get a validation error. Internal drawable creation failed. Important to note is that this error isn't coming from the like the validation layers or anything like this. Also, wow, this is a lot of symbols. This is like my first time debugging on this computer, right? So clearly some things don't quite work. The amount of function calls to display an assertion is pretty insane. Yeah, so the issue is that the driver, so normally the validation layers call the debug callback if something goes wrong. In this case, the driver was gracious enough to like call a callback and tell us what is going on. The only issue is that the error is really obscure. So I wasn't sure what to do about this up until I googled it, and turns out that the first answer is usually Stack Overflow, and it says, hey, this is a problem with GLFW, where by default GLFW initializes an OpenGL context. So NVIDIA drivers are peculiar. They are the only driver I know on desktop that does this, where they have a single driver that implements both OpenGL and Vulkan, and you can interoperate between these APIs on a sort of tighter level than you can do this in like as per spec, right? And I don't like this decision at all, but it's up to them. Maybe they thought it was important. But the upshot is we have to tell GLFW we don't need OpenGL, or we don't need any API, for that matter. And then hopefully things work. Whoa. So it still hasn't terminated my debugger session. So I had some text highlighted in the console window and it could not kill the console window because of this, and it could not. Alright, anyway. So that was easy to fix. So we have a triangle, now we need a mesh. Before we add a mesh, okay. So before we add a mesh, I was talking last stream about the fact that we are starting to use extensions. Extensions prove to be painful to use with default Vulkan SDK. We worked around this last stream by dynamically loading the entry point, but we want to use one more extension today. So at this point, I kind of would say, hey, okay, let's just use an extension loader. I said before that we aren't going to use third-party Vulkan libraries, but let's, break the rule and add an extension loader. So I have a library called Volk that we will add as submodule, and I also have a library called Mesh Optimizer that we'll use today to load a mesh that doesn't have anything to do with Vulkan, but might as well add the submodule. Volk is a very simple... Wow. Alright, that's kind of broken. Interesting. Okay. So Volk is a simple library that serves several purposes. One of them is it supports all of the extensions that Vulkan SDK exports, and it can dynamically load them. The other purpose is when you use Volk, you aren't linking to Vulkan 1 DLL, which means that it's much easier to say, hey, what happens if you want to support other APIs, etc. Why are these file names empty? Oh, these are the git ignorers, right? So this is like a new computer. I thought that... I thought that I switched developer mode, which should... Yeah, show file extensions. Alright. Whatever. Windows is weird. So, yeah, so it doesn't link to Vulkan 1 DLL, which means that it's easier for you to say, hey, if you don't have Vulkan on your system, what should we do? Maybe you want to display a nicer message to the user. Maybe, I don't know what you want to do. So let's just add Volk, extern Volk. That's it. When you use Volk, you should include it instead of the Vulkan headers. So let's do that. And then our code still compiles, but now the crucial thing that we need to do is we need to initialize the library. The initialization is done in 2 or 3 stages, depending on oh, I don't have... Alright, yeah, I'll need to set some things up later so that the workflow is better. So yeah, so you need to do initialization in multiple stages. The first stage is Volk initialize, which initializes the library, just finds the Vulkan loader, figures out where the entry points should be. This can fail if there is no Vulkan on the system, but we aren't really handling errors. So then we can create the instance as usual. Then we should tell Volk that we have initialized the instance. And this is basically it. The other thing that you might want to do is you might want to say Volk load device after you have a device working, but we don't really care about this. This helps performance a bit. We will not be concerned with CPU side performance at all, because we will be doing a very, very small number of draw calls due to how our render will be structured. So that should be it. Let's see if the code still works. Alright, the code still works. So why did we even do this? Well, here's the thing. So we were using this debug callback extension, and we were loading, I think I tried to not do this on stream last time, and we hit a problem where Vulkan SDK didn't import this symbol. So we are doing this thing where we are dynamically loading things. We don't need to do this anymore because Volk will do everything for us. So basically, whenever you want to use an extensions with Volk, you just use it. Of course, you still have to ask the instance for this extension when you initialize it, but you know, it doesn't require any further steps. So that's good. This means that we can now use extensions easier. I wanted to do a small cleanup thing where we were still using this window width stuff, and we didn't have to do this anymore. So I just wanted to remove this to clean up the code a bit, because we forgot to do this last time. So I should do this. I should do this. This code is slightly weird. Maybe this is why we didn't do it last time. Okay, fine. Oh. It doesn't really matter much. Let's just, yeah. All right. So our goal today is to render mesh. First, let us find the mesh that we will start with. I want to start with a bunny. Hey, Windows doesn't. Oh, come on. Why does it? Interesting. Huh. Farm Manager seems to be kind of broken. Maybe I should have gotten a new one. I think there are some new Windows stuff that might have destabilized it. Okay. Really? This is the problem with having a fast computer. This is like a seriously fast computer. But the problem is if your software is seriously slow, having a seriously fast computer doesn't seem to compensate. What is even going on? Is the stream fine? Stream seems fine, okay. Alright, Windows, Visual Studio like thingy is also not, I guess, a shining example of fast software. Alright, so that's the mesh that we will try to draw first. Oh, actually, you know what? No, I like this mesh more. Is it bigger? No, it's slightly smaller. It's fine. Like a YouTube stream is not a good stream without a cat, right? And let's be honest, we were neglecting our cat duty. So let's fix that by loading a cat. Or rather a kitten. So to display mesh, we need to do a few things. First, we need to load the mesh, we need to create vertex buffer, index buffer, all that stuff. This is the usual things that are not really related to Vulkan in any way, shape, or form. And then the other thing we need to do is we need to load the data for the mesh into Vulkan accessible memory. So we'll need to allocate some Vulkan memory. So normally, and there was already a question about this on chat, so normally you should write a memory manager for Vulkan or use AMD's Vulkan memory allocator library, which is an excellent library that simplifies Vulkan memory management. You can just say, hey, can you give me a chunk of memory, and it will give it to you. We will not be doing that because we are trying to not use third-party code. I mean, I know we've just used the extension loader, but without an extension loader, every single extension line would have to like load things dynamically, which is not fun. And also the extension loader is not complicated. Let me just like I really have to fix this. So let's just look at this code very, very briefly. Vulkan initialize, here's what it does. It loads the Vulkan 1 DLL dynamically. It retrieves the function that has to be used to load Vulkan extension stuff and also Vulkan core stuff from the library. And then it calls a helper function that just says, hey, for every single function pointer, let me just load it by name. That is it. There's no magic here. There is some magic in the fact that this code is automatically generated from Vulkan spec, and there's like complexity there. And this code works with any Vulkan SDK, regardless of how old or new it is. For example, there is like RTX features somewhere here. Yeah, like this stuff, right? But this library got support for RTX before Vulkan SDK got support for RTX, but it still worked fine, right? But there's nothing interesting going on here, right? So I don't feel too bad using this code because this is one line of really boring code that I'd rather just not write on stream, right? Comparatively, the Vulkan memory allocator library is not boring code, it's interesting code, and I'd rather write interesting code on stream. But also we won't even need to use that because of the way how we'll have to structure our renderer for our renderer to be able to be efficient in the sense that we'll drive our submissions from GPU at some point, and for all of that we kind of will have to do large allocations ourselves, which means that we don't really need Vulkan memory allocator. But if you are writing a Vulkan app, otherwise you should definitely use this. It's made by AMD. It is I already closed it. It's made by AMD, but it's cross-vendor. It works on, I heard it works on Android. It definitely works on PC regardless of the vendor that you are using. So this library is great, but we are not going to be using it because A, we don't truly need it, B, it does interesting things that I'd rather do myself here. So there's that. So let's start by just loading a mesh. And I guess before loading a mesh, let's just add Mesh Optimizer. So Mesh Optimizer has an OBJ loader, which we will be using today. It technically isn't part of the library per se, but it is too convenient not to use because I don't know what we would be doing otherwise. And I was thinking before about the fact that this parser is pretty good for simple cases, and it would be really nice to be able to just use it elsewhere, but it's not technically part of the library. Maybe there should be a separate library that just has this loader, and then maybe I should add support for materials and stuff. I know there's Tiny OBJ loader, but as I covered on stream previously, Tiny OBJ loader is significantly slower than this one, and I like performance, especially when we work with with large meshes, when we work in debug, etc. Anyway, so there is that. So we have added this code. It now compiles. Let us, what is resource files? Come on. Visual Studio likes to put, this file isn't even there. Visual Studio likes to put things into random folders, and I don't. Why is this, the structure is just messed up? Why? Man. Right, software. Alright, this is, okay, now it's nicer. So yeah, let's see if things that we have just added compile. Oh, that's not nice. I should not be doing that. Does this even warn still? Oh. No. Visual Studio has Clang format support, but it's so badly integrated that it's impossible to use. I don't know, they haven't... I don't know if they really tested this, because I tried to do it. I use Clang format for Mesh Optimizer, and it's like really painful to edit source with this Visual Studio thing enabled. Because it does like random formatting decisions for you at random points in time as you edit your code. It's insane. All right, so yeah, so we had the warning when compiling obj parser because it's not really a library right now. All right, so let's start by loading a mesh. Then we will talk about Vulkan stuff, but let's just do mesh stuff first. So we'll need a mesh. No. We will need a vertex. For now, let's just say that the vertex has a position, normal, and texture coordinates. This is inefficient. We will optimize this later. A mesh is a vector of vertices and a vector of indices. Or I guess you might want to use this. Right, and then we need a function that loads a mesh from file, say load mesh, where we tell it path, and we, well, I guess this, right? So now we need our obj parser. So let's set up more include paths. Wow, this window is not very useful. So the obj parse right now is in the demo folder, you know, that's fine. And let's also actually add mesh optimizer because we'll need to use functions from that. I could just like copy this code from mesh optimizer. This is not even Vulkan, but I want to also verify that I kind of like that the library is useful enough that I can just write stuff from memory without worrying about this. So we will need to include, let's just do it here. It's kind of weird to include things in this order, so let's move this here. So we'll need an obj parser, and also we'll need a mesh optimizer. All right, oops. Obj file if obj parse file path return false. This means we couldn't load the mesh. Now the obj file has a bunch of obj data in it, exactly how an obj file would have it. So we need to convert it into something that's more meaningful. So let's first create Vertex Buffer. This will be unrolled, like no indexing, just 3 vertices per triangle. We'll fix that part later. So we need a file f size that's fine. I think you should divide it, oh no, by, right, so for each face, for each triangle, there's 3 elements. Okay, all right. Obj file is an interesting structure. It uses 3 separate index buffers essentially, which hardware generally doesn't support. So we'll have to deal with that. Right, so the way it works is there is a vertex position index, which is obj file f I times 3 plus 0, and then there's a vertex texture index, vertex normal index. And then these guys can be -1, which means there's no texture data. So then we just need to say, hey, okay, the x is file v of vi times 3 plus 0, because there's 3 components. Right, and then same thing for normals, except that this is a different array. And then same thing for texture coordinates. And obj also has 3 texture coordinates per vertex, but we only really need 2. And then the thing is, if one of these guys is -1, then we should just substitute dummy data. This means our normals can be 0, which is weird, so let's just say that 0, 0, 1 for completely arbitrary reason, and then texture coordinates could be absent as well. And then this is our vertex buffer. So then I kind of want an index buffer as well. So I need to generate an index buffer from these vertices. There is a function in Mesh Optimizer for this, of course, which is called, it's like several functions because it's important. So to do this, we first need to generate a remap table. It's really fun. We'll be writing all this code with no way to test this code, and then we'll like run this code and see what happens. So there's no input index buffer, and I have this full array of data as an input, and then there's a vertex buffer, and then there is that, and then there's this. All right, and now we should be able to, this should return us the, do we need it? Yes, we do need it. The number of vertices that we actually, that are unique across all of the triangles, which is what our mesh will be. So now we can do result vertices resize, unique vertices, and result indices resize vertex count. This is slightly confusingly named, but that's fine. It's like triangle count times 3. Should really be called index count, really, because this is kind of what it is. So let's just rename that. So this is less confusing. And then this can actually be vertex count. Alright, and now we can do mesh opt generate, no, like remap vertex buffer. Well, yeah, where we tell it that we need to fill the vertex buffer with data that is retrieved from the source array, and we need this number of vertices with vertex structure using the remap table. And then we need to do the same for index buffer, but the parameters are slightly different. So we need to give it the source indices, which we do not have. So that's 0. And then the index count, which is index count. And then just the remap table. So this is it, I think. We have mesh, so that's fine. Now we might want to optimize the mesh for GPU, for more efficient GPU rendering. I'm leaving this to do because I want to render the mesh first, and also I would like to, as part of the stream, just do a sanity check on whether any of this stuff is actually important for performance, which it is, but it would be nice to just have numbers that say, hey, GPU performance was that, and then we optimize the mesh and it's now that. So yeah, this is just, we could, instead of doing this, we could just say, oh, you know what, let's actually do this. So this is the path that is indexed, so that should generate fewer fewer vertices, sorry, which is nice for GPU performance. But what we could also do is we could say, no, okay, let's just render a mesh without indexing, and I still want an index buffer. So I will just say that for for each triangle, the index is just 0, 1, 2, and then 3, 4, 5, etc., etc. So this is like an inefficient way to do this, of course, and this is a more efficient way to do this, and then you should really call a few other functions to optimize the result. All right, so we might have our mesh. Let's load it somewhere. Doesn't really matter where. At some point, we will start refactoring this code and moving this code into like separate files and separate like structures or whatever, but for now let's just keep the code flow super linear so that it's super clear what's going on, like nothing to confuse us. Yeah, so whatever, let's just load the mesh here. We already use RC, right? All right, load mesh. Mesh. So I haven't copied. Let's just do it like this for now. So we'll pass we'll just pass okay, the mesh path as a command line argument. For now, it's mostly because I don't want to, I'll add something to the repository, but these files are all like multi-megabytes, so I don't know if I want to do this, or maybe I do and it doesn't matter. But for now, let's just say, hey, let's just specify command line argument, call it a day. All right, let's see if this code compiles or works, or there's a warning. Clearly, we don't know if the code works yet because, right, we only loaded the mesh into some state vectors. And also we forgot to return true, so this is a really good warning. All right, so maybe this code works, maybe this code doesn't, who knows. The more important thing is now we need to actually deal with the Vulkan stuff. So to deal with the Vulkan stuff, we need to do two things. One is we need to actually have this memory available in Vulkan accessible objects and memory and whatnot, right? And the other is we need to start using this in the shader to somehow pass this data to the shader, right? Hopefully that makes sense. So yeah, I'll try to do this in a few stages. So first thing is, right, so first thing is we need to upload the data to some object that Vulkan knows about. There's a more complex way to do this that is actually the correct way to do this for dedicated GPUs, where the buffer will reside in GPU video memory. However, this is more code. We will not be doing this today, for now at least. Maybe if we'll have time, but I don't think we'll have time for that. So we will just create a Vulkan object that we can write to directly from the CPU, which is actually the correct and optimal path for mobile devices and for Intel integrated GPUs as well, because there the memory is unified, so you don't have to copy it into dedicated memory. So from the get-go, this code will be like, might use it several times because we'll need several buffers. Today we will need two buffers. We'll need a buffer for vertex data and a buffer for index data, and then in the future we'll need more buffers like this. So let's just create a helper for this immediately. Let me briefly look at chat. Could it be that TinyObj loader is slower because of C++? Yeah, this is part of this. They have like state vectors and stuff like this, but also it's just not written for performance. My obj parser is written for performance. VKDoom 3 also uses its own path. Yes, so so Roblox has, like the company I work for, Roblox has a Vulkan renderer. We don't actually use VMA. We have written our Vulkan renderer before VMA was a thing. And I think the same applies to VKDoom 3. It was just written before VMA. And now there's like not a strong incentive for us to move away from that. Our Roblox allocator is like really simple, really straightforward, and it serves as well. So For now, yeah, we don't use VMA, but there's production Vulkan apps definitely using VMA, so don't hesitate if you write a new Vulkan app. Feel free to use VMA, it's perfectly fine. It's a good library. So, buffers and Vulkan. So, there's two things that we'll need. There's several things that we'll need. So, we'll need a buffer object. This is what we can use to actually bind it to a shader and things like that. We'll also need a memory object. Wait, how is it called? Alright, I forget how it's called, but we'll need a memory object. We'll fill the type later. So in Vulkan there's a difference between memory allocations and objects that reside in them. You can and should have several large memory allocations and then have a bunch of objects that kind of share space. We will not be doing this because our buffer objects, due to how render will be structured, will be large anyway. So we don't really need this. But this is what VMA will do for you. The other thing that I want is I want a pointer, right, that, well, why is it const? That we can use to write data to this buffer, right? And then I guess I'll need size just to just to check that things work fine. So this is kind of our structure. This is what we want. I don't think we'll need more than that, but who knows, we'll see. So let's add functions to deal with the structure. So we'll need create buffer, and I guess we should, it's the same thing, should we handle, let's just not handle errors, you know, who cares. So we'll need a way to create a buffer of a given size, right? And then likely we'll need the device. And then we'll need one other thing that we will grab once, that I will talk about in a second. And then of course we'll need to be able to destroy buffer. Oops. Result is a weird buffer name, weird name for this, but what am I calling this in destroy swap chain? Swap chain. That's a better name. All right. So creating the buffer requires several stages. The first thing you need to do is you need to call create buffer object, which is confusing because we don't have the memory for this buffer object, but there is a point to this. So to do this, we need to do the usual create info dance and write this, and then vk buffer create info, vk structure type buffer create info, and then we need to specify a few things. So I think the SKU family parameters here, we dealt with them like last stream and the stream before this. I think we don't need this unless you want to share the buffer between multiple queues, which we don't want to do. So we just want an exclusive buffer. Could be wrong. So the important things we need is we need flags. We don't need. This is for partially resident buffers. We need the size, right? Obviously. And the other thing is we need usage flags. Usage flags are important. And for this, we'll just pass buffer usage flags usage and just like forward this. Alright, so here's our buffer. Of course, we're not done. So if this was OpenGL or Direct3D11 or Metal, you would be done. This is Vulkan, so you know you're definitely not done. So the next thing you do is you say, hey, this guy creates a buffer object that doesn't have memory back in it. It's just a dummy handle. So then you say, hey, given this buffer, say how much memory does this thing use? And what this tells you is how much memory you need, how should it be aligned, which is really important if you're implementing your own sub-allocator. So one buffer can be, maybe it's like 5 bytes, but it has to be aligned to like 256 or 1024 bytes. So you have to give an appropriately aligned memory. And the other thing is this memory type bits. Memory type bits is a way for Vulkan to deal with a single API. They're trying to cover many use cases. On integrated GPUs, there's generally only one type of memory, which is shared between CPU and GPU. On dedicated systems, dedicated GPUs like we have right now, oh, I forgot, I guess, to say this, but I guess I did say that we are using a new computer, but yeah, it's like an NVIDIA graphics card, right? So here I have system memory and I have video memory, and these are separate chunks of memory. GPU can read from system memory. These accesses are slower. CPU generally cannot write directly to video memory. Otherwise, we would just do that and be done with that. So that's unfortunate, but that's what it is. On AMD systems, there's a third chunk of memory. On AMD systems, there's 256 megabytes of video memory that are mapped for direct access of CPU, which is really nice. And you could copy data to there directly. It's only 256 megs, even if you have like an 8 gig video card. But this is really convenient in certain cases. We don't have an AMD GPU, unfortunately, so we'll have to deal with system memory for now. Yeah, so this basically tells us, hey, what kind of properties should the memory that is necessary for this buffer satisfy? And it's using memory type. I think it's using this guy. Yeah, so it's using, I think this is basically this type, not just an opaque bit field. Yeah. Let's see if I'm right. And then we will be able to actually start allocating memory, I guess. So yeah. So we need the vertex buffer and we need an index buffer, and I kind of want to just create a large, like say 128 megabytes of vertex data. So, and we need to say that we will be using this as a vertex buffer. And I want an index buffer, and let's also say that we need 128 megs of index data. This will change a bit, but whatever. And obviously our mesh could be larger, could be smaller. I don't want to handle the case where it's larger, and I don't want to handle the case where it's smaller, because today we just have one mesh, but at some point on the stream we'll have more than one mesh, and I will want to pack all of this data into a single buffer object, for reasons that will become clear way later on the stream. So let's just say 128 megs of geometry, well, 256 in this case is going to be enough for everybody. Now let's see what we have. So we have 128 megs. The driver tells us that we need to align it to 56 bytes, which is not really a problem in our case, but this alignment could be much larger depending on the type of the resource. And it also says that it wants a memory type bits of 1665. 1665 is not a meaningful value. However, if you look at it in hex, I wish Visual Studio had like a binary view. Then it becomes clear that I am wrong. Well, right, yeah, sorry, this is definitely not this enum. This is some other enum. I forgot which enum it is. It's definitely not this enum, right? Because I'm not even saying how I should. Never mind. What kind of enum is this? Oh, this is not an right. Okay, never mind. I think I remember this now. We'll look at the spec just to make sure, but I think I remember this now. So the way this should work is this. You can ask the physical device what kind of memory properties you have. And this will tell you, and we'll look at this right now, this will tell you what kind of memory heaps and stuff does the device have. And we should pass this to this guy, vk physical device memory properties, because this is, I think, how you're supposed to interpret this index. Maybe. I should really just look at spec for this, but... So let's do this again. Oh, great, it's already... Alright. So let's look at what the device provides us with. Oh, okay. Yeah, I think this is correct. Should I even use this? I forgot how this works. So here's what the NVIDIA GPU tells us. NVIDIA GPU tells us that we have two memory heaps. So one memory heap is video memory, one memory heap is system memory. So as you can see, I mean, it's hard to parse these numbers because they're really large, because they're in bytes. But this is basically 8 gigabytes. And this is basically 32 gigabytes. So I have 8 gigs of VRAM and 32 gigs of system RAM, right? And then when you allocate memory, you don't allocate it out of a heap. Unfortunately, you allocate it from a memory type. And there's 11 memory types here. And they map to indices, and some of these entries are the same. And this distinction is sort of important, but I will not go into why. There's like a reason why. But what you are supposed to do is this. So I think this memory type bits say which types are compatible with this buffer object, right? So this value, oh, let's use calculator. Calculator, one of the biggest improvements since, I guess, I forgot when this was added. Was this Windows 10? I feel like this was Windows 10 or maybe Windows 8, but I don't know how we lived with the calculator before this, because honestly this is just really good. So this value has 4-bit set, right? Which means that we are being told that we can use one of the 4 types associated, like listed here, to allocate this memory. Let's look at which ones these are. So the first one, which is this, which is heap index 1, which is our system memory heap, and some flag 0, doesn't matter what these are now. Then number 7 rather, this was number 0, so this is number 7. So this is the video memory pool, and all property flags 1, whatever these are. And then also, so this is 7, 8, 9, and 10. So we are being told that we can use any of these guys to allocate this memory. Yeah. So let's now look at these property flags. So these property flags are actually the bit masks for the stuff that I was talking about here. So let's look at this. So the only memory type that we are allowed to use here that deals with video memory is heap index 0. This is video memory. Property flags 1. This is device local bit. Device local bit means this memory is really close to the device. In this case, this means video memory, right? If in an integrated system, all heaps would be device local, so like all memory is really close to the device. This is the fastest memory to access from the device. We are not going to be using this today because it requires more legwork to get there. And then we have 3 memory types that correspond to system memory with property flags 0, 6, and 14. 14 is 6 plus 8. So basically we are saying we can have none of these flags, or 6, which is 2 plus 4, which is host visible and host coherent, or we can have host visible, host coherent, and host cached. So in general, for system memory, you want host visible and host coherent. Host visible means you can write to this memory from CPU and also read, but we don't need it right now. Host coherent means that whenever you do a write from a CPU memory and then submit a command to the GPU in a command buffer, you don't need to do extra operations to make sure that this memory is like visible and there, right? If you're asking for host visible, coherent, and cached, which is this one, you're saying, hey, this memory is cached on the CPU, so it uses CPU cache, which means it's faster to read. I wasn't even talking. I guess I didn't mean. Sorry. I was meant to say that if you don't use coherent memory, then you're saying maybe this is using a CPU cache that is not coherent with the GPU memory, which means that you have to explicitly flush the writes that you do to this buffer, which we don't want to do. So in general, you should prefer just host visible and host coherent. For people who know what write combined memory means, this is that. Like host visible and host coherent is basically write combined, assuming you don't have host cached. This combination isn't guaranteed to be available by Vulkan, but in practice it's available on every single device that I have seen, and it's basically, as far as I know, you never compromise. Like, there's never a reason for you to just use host visible without the coherent bits. I could be wrong on this, but as far as I know, there's like not really a reason to do this. There is a combination of host visible, host coherent potentially, and host cached, which is useful for reading data from GPU. Like if GPU writes to a buffer, you want to read that, but we aren't going to do that ever on the stream, so that's fine. The upshot of this is that we get the memory type bits, and then we need to iterate through its memory types, and then we want an allocation that has both of these. And if it's not there, we will just, I don't know, it will not work out. But if it is there, then we're good. So let's make a function, select memory type, where we will pass this guy. And then we need the memory type bits. And then I want a function that's like memory property flags. So we need to go through all types, and then if the memory type bits has the bit set, and I guess memory properties, memory types I provides us all of the flags that we need, then we can just return this one. Otherwise, we'll assert no compatible memory type found, and return. Return something that's just like not valid, and something will crash. In practice, you may want to handle this in some ways. For example, generally speaking, even in production renders, you kind of know which flags you have to. What we do in Roblox is we have a function like this that has required flags and then also optional flags. And then we first check if there's something that has both required and optional, and then use that, and otherwise we just use the required ones. But we don't need this for now. So given the memory requirements, we can now select the memory type index, which is select memory type, memory properties, memory requirements, memory type bits, and for this we are saying that we need property host visible and property host coherent. Alright, and now we need to allocate memory, finally. So to allocate memory, you call shockingly vk allocate memory. So device, we need allocate info, and then vk device memory, this is what it was called. How are we doing this on, how do we do it on time? We are doing fine on time. We might be able to get this done. So let's see. We basically need to say how much memory we'll need, which is just the memory requirements size. Note that the size that this guy returns us could be larger than the size that we requested, because it could align it to some high value or whatever. Also note that we aren't specifying the alignment here. The alignment from this guy is only necessary if you share a single memory object between different buffer objects or texture or like image objects or whatever. So there's that. So we allocated memory. Now I want to map this memory to get a CPU visible pointer to this memory. Oh no, I first should, does it matter? It doesn't really matter which order I do things in. So then I want to do an operation that's called binding memory to an object, which is the operation that ties the memory and the object together. And you can specify the memory offset. This is useful when you share the memory object between two buffers. You can bind a range to one buffer and then another range to another buffer. But for our case, the offset is always 0, and then this can fail, and then I have no clue what to do when this thing fails, so we just do that. And then I want a CPU visible, so we have this guy, should be ready to use now. We have this guy. We don't have this, so this is a CPU pointer to the memory. So to get a pointer like this, you need to map memory. So given the memory at an offset 0, I want to map a region of the size. I guess I could use whatever size, that's fine. Flags, I don't know what these are. Oh, I think this is some placeholder that, you know, okay, memory map flags. I think this is not actually useful, yeah. You can tell on Vulkan when flags are there or not. So all Vulkan flags that are like an association of bits, these are all just VK flags, because which is just like uint32 or something like this. Because in C there is not a way to do a type safe enum that has bit flags in it so that you can like OR 3-bit values and get the same type. However, in Vulkan there is a nice convention where if there's ever an enum that has entries that is a bit mask, then first there's a declaration of this enum in the header, and then there's a type def for the flags. So here you can clearly see that the pipeline stage flags enum is not empty. There's a lot of valid values. And the memory map flags enum appears to just be empty because this is some placeholder stuff for later. Like they think they might want a flag value to like extend this API in some way. So that's 0, and then we need data. Alright, and then we are done. We basically just need to fill these guys. Result, memory, result, data, result, size. Alright, and then we need to destroy the buffer. To destroy the buffer, we need to deallocate the memory. Destroy memory. Free memory, right? Oh, we need a device pointer again. You don't need to unmap the memory. Oh, and also unlike OpenGL and Direct3D, you don't ever need to do an unmap operation here. There's one case where it's kind of important for performance that you do this, which has to do with this AMD 256 megabyte memory chunk that I talked about earlier. But otherwise, you could just get the pointer and just always use this. In OpenGL, in later revisions, there is a concept known as persistently mapped memory. This is that. In Vulkan, in general, my recommendation would be you only ever use persistently mapped memory and just call it a day, because it's faster for the driver to deal with. Maps and maps are slow on some drivers, and it's also way more convenient for the programmer. All right, and then we need to destroy the buffer object. And then we, all right, and then here we need to destroy the stuff that we have created. So let's destroy buffer VB and IB. Let's see if this code compiles. It doesn't even compile. Okay, let's see if this code works. All right, we don't have validation errors, so that's nice. So we have successfully written a page of code that doesn't have validation errors, but we don't know if it works yet. So in theory, we should be able now to just say, hey, what if we copied into the Vertex Buffer on GPU accessible memory? What if we just copied the vertex array, and then there's like this times is of vertex, and what if we just copied index data? And then it would be nice for us, I guess, to assert here that like VB size is greater or equal than this thing. All right. And then this thing. And in theory, we have our data available to the GPU. Now we want to use this data. So there's two ways to do that. And maybe I want to start with the old way. Or maybe I just want to directly go to the new way. Let me think about this for 1 minute and also read chat. I am from Russia, to somebody who's asking. 125%. Oh, sorry. I forgot about the font. Hopefully it's better now. Assuming you meant like font on the Visual Studio. What do you think of object-oriented programming? That's kind of a rant for another day. Not a huge fan of OOP, but I don't... Yeah, I'm not a huge fan of OOP. I use it, like I'm like reasonably comfortable working with object-oriented code bases. But there is a point in object-oriented programming where you take things too far, and whenever this happens, I kind of feel unhappy. But it's an evil that is there that you have to deal with, because everybody writes OOP, right? If you were to choose this for yourself, then I would not recommend this. You'll notice the code that I'm writing can't really be called OOP. There's like structures with everything accessible, etc. That's the style that I tend to use normally myself these days when I can. If I work in the context of an object-oriented code base, then I kind of follow the rules and the style, right? But yeah, not a huge fan of OOP. It depends on what you consider OOP, but the canonical, this is like super not OOP in the canonical definition of OOP. Or OOP, as some people call it. Maybe I should call it OOP. Alright, so that, right, so how are we gonna do that? It will be faster to do the old thing, to get something on screen, and then we can change it. which is not a very satisfying thing to do. But you know what, let's do this anyway. Yeah. So first, very briefly, let's try to just render a mesh on screen. To do that, we will use the old way of specifying vertex data, which we will stop doing. So this is temporary, because this is not how I like to do things, and this is not how I want to do things. However, this will get us something on screen like now, very quickly, and then if we have time till the end of the stream, we will implement the new way. So we need a vertex stream essentially, which is binding 0. Do we even have the vertex structure here? We don't. Alright, you know what? So this is like what, 8 floats, right? So let's just hack things together for a bit. Okay, vertex input rate. Okay. And then we need attributes. So this is our position. So this is how you would do things in, you know, like OpenGL, Directory 11. There's 3 attributes. One is 3 floats, the other one is also 3 floats, and the last one is 2 floats. Offset 0, 12, and 24. And the vertex is 32 bytes, right? And then when you initialize the Vulkan, this is totally not gonna work like this. Let's just, all right. And then when you initialize Vulkan pipeline state, you say, hey, can you figure things out so that the objects are in, or the like the inputs to the shader are coming from memory buffers with these formats and stuff like that, right? Vertex. Input. Oh. And then you say that there's 3 attributes and there's 1 vertex buffer, 1 vertex stream, and then when you do a draw call, and this will not work yet because we need to change the shader, but you need to bind the vertex buffers, and the 1 vertex buffer that we are using. Offsets. I don't think I can specify them as null. And then you bind an index buffer, which index buffer is, we'll need to do this as well. IB buffer 0, VK index type 32-bit. We'll switch to 16-bit indices at some point, but definitely not now, because I want to handle larger meshes. And then instead of VKCMD draw, we say VKCMD draw indexed. Command buffer, index count, index count, index count. So indices size is the index count, 1 instance, no offsets. Oh, the other thing I forgot to do, which is kind of important. Well, is it? I don't think it's too important. Let's not do this for now. Let's look at this mesh. Yeah, this is fine. Let's just not touch this for now. All right, and the final thing that we need, and then if things work, then we'll have time to do things the right way. Oh wow. Oh wow. Whoa. Oh. So this is the syntax highlighting extension that I installed. Who thought that this color is readable? Really? Like, this is a super bad color. Like, it sort of hurts my eyes a bit. Yeah. Okay, whatever. So and does not support comment highlighting in C style, in C++, like C style comments. All right. So this is a bad extension. I should try. There was another extension by Sasha Willems that I didn't want to do because it felt like it maybe was more than just syntax highlighting. Oh, is there just like some shader stuff that's not GLSL? No. Yeah, so there was this, which, let's see if it even, oh, just context menus. Does it even do syntax highlighting? It's not super clear from this, but it looks like it does. Let's install Sasha's extension because I just can't read this. This is not a good, all right. How do I delete this one? This one, like, just no. It's like better to work without syntax highlighting than with really bad syntax highlighting. Oh, I prematurely started Visual Studio again. This is why people like Jonathan Blow and Casey rant about the state of software all the time. This is a really fast computer. You cannot argue that it's a slow computer anymore. It should do things like copy a bunch of files to like a bunch of folders without me waiting on the progress bar for like 20-30 seconds. I don't know. It felt like a long time. Okay. With Sasha's extension, we don't seem to have syntax highlighting, period. Yeah. I mean, it didn't say so. Maybe Sasha was using some other extension in his screenshot. Alright, you know what? It's better to do things like this even. So... Okay. So in our pipeline state, we said that we have a position. Yeah. Which is it like location 0 or binding 0? I forgot. Normal and text chord. So for now, let's just do direct output of position, and then I kind of want to see something on screen that's not just a boring single color. So let's do invec for color and do color here. And here we'll have an out vec for color, This is a bit hard to read, so let's do it like this. And color will be, say, normal. Well, let's talk like 4. So it's normal times 0.5 plus vector 0.5 and 1, 0. Let's see if this compiles. It doesn't. Yeah, so maybe it's not binding, maybe it's location. PRV requires location for user input output on the line 21. Yes, that is true. That is true. Names are very much not used in SPRV. Layout location 0. All right. I don't know. Maybe we'll have a triangle mesh on screen. Haha. Hello, Kitty. What's up with the ear? It looks like the ear has been clipped by some clipping plane. Let's fix the kitty. Oh, right, because Z is probably between -1 and 1 in this mesh. Yeah. So let's just shift it and hope it's fine. Whoa. Yeah, right. That's actually expected. Cool. All right. Congratulations, we have rendered a triangle mesh. This wasn't that hard, right? We wrote a helper for buffer creation, so now creating a buffer should be really easy. So that's really nice. This mesh is coming from system memory, so it's not the most efficient way to drive the GPU, but it's fine. So what's up with the kitty being all weird and stuff? The thing's up is this. We do not use backface culling right now, so we're rendering every single triangle of the mesh. We also do not use a depth test. So what you're seeing is, with no depth, you're seeing an intermixing of triangles that are in the back of the kitty with triangles that are in the front. And triangles that are in the back have a normal that points the opposite way, so you see this, you know, sort of weird and not that adorable, but, you know, output. All right, good. So that's really good. So the thing is, to do things really right, I need to do timing. But we have 40 minutes. I want to end coding in like 40-ish minutes. But I guess I only wanted to do I only wanted to really do one thing. Well, I wanted to experiment with smaller. Let me strategize. I'll look at the chat for a bit. Zoom plus PBR response in single screen. Are you referring to the code thing? Then yeah, I did this. Yeah, sorry, I forgot about this. With 1080p stream, I think people who are on smaller screens or on 720p like stream, you know, display settings, the code is not very readable. I had the font size bumped up on my Surface computer, but not here. All right, so I kind of wanted to do a thing, and this might mean that we don't actually measure whether it's slower or faster or anything. But I mean, that's the future, so maybe it doesn't matter. I don't know. All right, you know what? Fine, that's fine. Let's just do things how I think they should be done long term. Just ignore performance for now. Oh, let's see if our indexing code actually worked. Okay. It's good that we have started with the path that does not use indexing, because clearly something is not right here. All right, let's see. So this I think is right. It's hard to mess up this call. So then it should return the number of unique. Yeah, it returns number of unique vertices. So then we resize it to that, to this. So it must be that one of these calls is messed up somehow. So when we destination vertices, vertex count should be the initial vertex count and not the value returned by. All right. I think somebody who was using this API ran into the exact same problem, which is why this comment is there. So thank you, you know who you are. All right, cool. Yeah, so we messed up the calls a bit. It's unfortunate that this function doesn't even warn you, but it's really not easy for this function to warn you about anything with assertions. It doesn't know. Yeah, you tell it a smaller value, and it just doesn't know. Yeah. Well, this assert could have triggered, but it didn't. No, it would never have triggered. Yeah. Damn it. Oh well, yeah, it's like impossible to fix this. Other one, yeah, okay, alright. I had to do entry that maybe should elevate in priorities to fix this interface a bit. All right. All right. So this means that we are actually now using the index buffer because it's, oh, we can even inspect, I wonder. Yeah. So here's the thing. With this mesh being in CPU readable memory, we should be able to look at like IB, which is our buffer, and it has a pointer to data. We should be able to say, hey, this is memory that's accessible by GPU. It's a system memory, but it's accessible by GPU. We should be able to say, hey, what are the first 12 values in this guy? And it's just a linear index stream. Oh, okay, right, yeah, okay. It just starts as linear, it's all good. Yeah, and this is our index buffer, right? So it starts as just boring, like, sequential values, but there is some. This is really not that good. What's going on here? Oh no. No, yeah, it's fine. It just starts weird. Okay, that's fine. Alright. So yeah, so we are now actually using the index buffer meaningfully. Cool. So here's what I want. I want to not use this stuff. Right now we are telling the pipeline object where the values in the vertex are. I don't want to be doing that. There's a couple of reasons. One reason is it's not compatible with mesh shaders. One reason is it's not compatible. It's compatible with some of the GPU stuff that we want to be doing, but it's not the best way to do this. On AMD, if you are hitting this path, you're actually being kind of slower than you would normally be. So there's like reasons to avoid this. To avoid this, what I want to do, let's do a checkpoint commit, okay? Because I'm scared it will like break things. Oh, right, I fixed the bug. Whew. Can I commit? I can't even commit from here because. All right. Let's do. I mean, it was just a warning, I guess, so we don't need to do this, but it's fine. So in theory, I can kill this, and then I can pull this, and then I should be able to, well, so yeah, we wrote like a bunch of code that works. Oh, well, yeah, you have to specify the mesh as a command line argument, but that's fine. Day 4, we have rendered a kitty. This change adds walk for extension within the mesh optimizer and does a simple mesh rendering using fixed function vertex attribute bindings. We aren't using device local memory yet for simplicity. Like, you know, long term, there will be a point where I think AMD was moving in this direction with HBM, was it, or something like this? And I don't know what NVIDIA does, but long term, I kind of want to say, hey, my GPU memory is like a cache. If I want to upload resources, I just upload them to system memory without worrying about this, like I just did. And then on the GPU, there is a magical thing that just mirrors parts of this into a large cache. Not like caches on GPU right now that are like half a meg or something, but there is like 4 gigabytes of VRAM, which is caching everything from system memory. And of course, stuff that you don't ever need to access on the CPU, you can just put there. But everything else, I kind of don't want to do the current thing that's necessary in Vulkan, where you manually have to copy things around. This is my, and then there's fewer differences between unified memory architectures and like discrete GPUs, where discrete GPU VRAM is just a very large cache. And I'm fine with saying, I would be totally happy with saying, hey, can you like vk prefetch memory something on this memory object after I create it, but I don't want to do more than that. So, but anyway, Alright, so let's start trying to do things the way I think things should be done these days. The way I think things should be done these days is I want like the structure vertex that's basically the same as the one on CPU. Yeah. I want to be able to just say, hey, can I like, where's my structure? Like copy this structure into GLSL code. All right. And then be like, I want to read data from this memory, from an array of vertices. Let's just declare an array of vertices. You can do it in Vulkan like this. You need to say that I have a buffer like this, and then be like, hey, can I like read the vertex from GL vertex index, which is a built-in variable that will be read from an index buffer by hardware. And then just, yeah, like position is a vector of vx, vy, vz, and you could declare vec3 here, or you could keep it like this. There is the reason why I'm doing this, which will become apparent maybe shortly, or maybe next time, depending on whether this will work. Oh, wait. All right, and vec2 text chord. You don't need these are just for simplicity to not change this code, right? So I kind of want to write code like this. Let's see if this compiles. This compiled. Here's what this means. And this means we don't need to be dealing with the thing that we just wrote here. This means the shader is fully controlling the vertex format. This means we can be doing funky stuff. Like there is a technique, OBJ files have 3 index streams. 3 index stream is kind of over the top, but maybe you have 2 index streams. So maybe you want to have 2 vertex buffers. And classically, the hardware will sample from them using the same index. But maybe I want to say, hey, when I'm sampling from the first one, I want to use the low 16 bits. And when I sample from the second one, I want to use the high 16 bits. This means I can have 2 index streams in 1 index buffer without paying the memory cost of duplicating vertices. And also, when we do, not if, mesh shaders, we will have to do things like this because mesh shaders can't use fixed function input stuff. So this is good for us. We want to do things like this. Also, we want to kill this comment. Here's what this means. This means we need to pass this buffer to the shader. We are not doing this right now. Now, normally in Vulkan, you should do things like this, like pass an object to the shader. So we are currently bind vertex buffers. Yeah, so we are currently doing this, which is part of this fixed function stuff. We should not need this. So long-term Vulkan API, my point is the long-term Vulkan API should not have this function. All right, everything should be buffers that you pass to shaders. Now, so normally in Vulkan, when you want to pass a buffer to a buffer object to a shader or an image object to a shader, you use this complex descriptor management layer, which you can do. I don't want to be doing this. I don't want to be doing this now for sure. It's questionable whether we want to be doing stuff like this long term. Well, there's a use case for this. But like the fact that descriptor tables are a part of Vulkan descriptor sets is a good thing. But there are specific cases where you might not want to be doing that. And also there are specific architectures where descriptor sets aren't a very good match to an architecture. Like I know that descriptor sets are a good match for AMD, not a very good match for NVIDIA. Don't know if it's a good match for Intel. I would not be surprised if it's not a very good match for Intel. I would not be surprised if descriptor sets are optimal for AMD hardware and no other hardware on existence. So, to simplify our life short term at least, we will not be using descriptor sets. Instead, we will be using an extension that is exposed by NVIDIA and Intel, is not exposed by AMD. So if anybody here wants to run this code on AMD, I'm sorry, we will just be breaking your breaking things for you. But yeah, so what we want, why is this thing still here? Isn't it thought surface swap chain. Okay, that's fine. Anyway, so the extension is called KHR, so it's not like a random NVIDIA extension. We will be using random NVIDIA extensions on the stream, just not now. KHR push descriptor extension name. This allows you to just use one function to just send data to the shader, send like an object to the shader. Really nice. You can use at most 32 as per spec descriptors. The device could expose more, but the spec limit I think is 32 descriptors. So this is what we will be doing. We will be doing this. Now, when you use this extension, first of all, let's run the code that we have right now, and we should have a validation error that should tell us, all right, retry, validation error encountered. Oh. What? Vertex pipeline stores and atomics. What? No. Is it because of this? Are you for real? No. How? What? I am not. No. What? Oh, No. What the hell? Wait. Alright, this is why I did the checkpoint commit. Because I have not done these things before. Wait. I'm not using stores from the Vertex shader. Whether storage buffer supports stores, I don't use that. Should I like specify this buffer as read-only somehow? Maybe that's what it is. Is it like this or something? I forgot. Is there like a read-only qualifier? No. There is definitely in GLSL, but I forgot how it's used. Read-only. Yeah, but where? Before? Same error. But it's read-only. Is it? Wow. Alright, so temporarily, let's unblock ourselves. This does not make sense. I think I'm not doing something right, or validation layers are not doing something right, or something isn't going the way I thought it should be going. But a lot of things can happen. So, to unblock ourselves, the validation layers tell us to request a specific feature. Let's cave in for now. Maybe I didn't put read-only in the right place now, and the compiler didn't complain. We'll need this thing anyway, so yeah. So the interesting. Validation layers think that my shader is writing to memory, is requesting a write to memory from a Vertex shader, which is not happening. But I don't want to debug this yet. I want to put it to do here. We aren't using this yet. Alright, so this is the error that I actually wanted to get to. So the error says the shader uses descriptor 0 with the storage buffer, but it's not declared in pipeline layout. So I talked about this in Vulkan, and I want to write a more generic way to deal with this problem on a future stream, but this will take time. We'll have to parse SPRV code. We will not be using SPRV reflection libraries, because remember, we are trying to not use third-party code. That's interesting. Volk was an exceptions where I'm like, it's super trivial code. We could just write it, but there's no real point writing it ourselves. With SPRV, there is a point writing this code ourselves, because this will give people an insight into how SPRV is structured. So, yeah, but like right now, essentially, when you create a pipeline, where is this even? Yeah, when you create a pipeline layout, you have to tell Vulkan what you are, like what resources are you expecting to pass to the shader. We are not doing this right now. The fact that maybe I should, can I like just delete these guys after I create the pipeline layout? All right. So yeah, so we have to tell Vulkan that we will be passing a buffer to the slot 0 or whatever it is, and also I think we have to tell Vulkan that it will come as a push descriptor. So let's do this. Here's one more create info, set create info 0 set layout, wiki descriptor set layout. Create info set layout account, set layout. All right. So it feels like redundant work, and in some ways it is. And you know, all of this needs a redesign, but some people make a mistake of looking at Vulkan and saying, yeah, obviously this is how things should work, and then designing their rendering abstractions around this. And man, I wish people didn't do that. Alright, yeah, so we need to tell Vulkan that we will be using push descriptors to just send like data to the shader without managing descriptor sets ourselves. And we need to tell it that we will be using at least one for now, input argument to the shader, where we will specify the binding. We will say that it's a VK descriptor type storage buffer. The thing that we have just declared in GLSL is called a storage buffer. But it's just a buffer that can be arbitrarily large and you can index however you want, and there can be more stuff here that's not just an array. We have just one of these, and we will say that we are reading this shader stage vertex. Wow. Having a faster computer does not make IntelliSense faster. IntelliSense is just slow. Alright, so yeah, that's done. Bitting count, array size. So we should do a pass-through code and just start using array size macro everywhere, because we didn't have it when we started doing Vulkan stuff. Alright, set bindings, set layout, create. I'm kind of hoping that I can like destroy set descriptor, set layout now. IntelliSense just gave up. It's like, man, I don't want to work with you. I don't know if I can do this, but if I cannot do this, this would be unfortunate, because then I have to destroy this object at some point, and then I have to create this object externally, and it's just gonna be a mess. But okay, let's see if this code even works, because it probably isn't. Right, oh yeah, okay. So, alright, let's try to destroy this. I don't know if this is valid. I also don't know why IntelliSense doesn't work. Is this a valid function name? Maybe it isn't. But for wiki create, it worked fine, right? Oh no, IntelliSense just is dead. IntelliSense just gave up. Alright. Oh no, okay. Wiki destroy. Okay, destroy pipeline layout. Wiki destroy set pipeline layout. Set. Script. Nah. Okay, destroy. Oh yeah, this guy. Why did IntelliSense not pick this up? Right. So I don't know. You know what? Let's probably device set layout 0. So I don't know if I can destroy a set layout immediately after seems like I can, so that's nice. So yeah, we are creating a set layout object and then passing it to another create function and immediately destroying this. Validation layers don't complain. I should really check what the spec says, because just because your code validates fine doesn't mean that it's correct. So we're passing it an array of set layout objects, and then there's a lot of text here, push constants, pipeline, layout may be used, resource variables must be declared, limit, Limits, compatibility nodes. All right, I don't know. This might not be safe. Validation layers don't complain, which is nice, but they might not be checking this at all, which is not nice. And I don't know if this is safe. If we hit like a crash in the driver, we will know. All right, so now what I want to do is I want to just say, can I push descriptor? For people who are familiar with Vulkan but have never worked with push descriptors, there are kind of like push constants just for descriptors. And then triangle layout set 0, and then I just need one descriptor for now. And then I need the vk right descriptor right set. Vk right descriptor set. Things really went downhill. I don't know why IntelliSense is so bad right now. Maybe push should be this is kind of this is way not as nice as push constants. It's just way more verbose. I mean, I'll need to think about whether it should be as verbose. I don't know if it should be. All right, so let's see if that worked. Right. Aha, okay, all right, so that was nice. So that was pretty painless. I mean, it was a bit painful, but it's because of this stuff. So yeah, that's roughly the same number of lines of code, I guess, but now we are passing this array directly into the shader and have the shader directly read from it. And there's still this read-only thing that I don't get. It definitely isn't. Is it like this? Was this the problem? No, clearly it doesn't work either way. So this is confusing. It seems like a bug to me somewhere. Is this a bug in GeoSlang or in validation layers, or do I just not understand the spec? Maybe I can't write GLSL code, I don't know. Alright, final thing I want to do. We have 10 minutes left. Let's just see if that works. So the thing you really want to do, of course, let me see if maybe on chat somebody just knows the answer. Yeah, so read-only buffer doesn't seem to work. Right? Like, yeah, so with read-only declaration, it says non-writable on the entire buffer object. I probably should tag the entire buffer, right? I probably should not be tagging just one field of that buffer. So I don't understand why why validation layers think that the pipeline requires stores. So before I put read-only, right, it was a correct validation. Like this, the compiler does not infer the type of the object. It just says you didn't say it's read-only, it might be writable, even if the shader doesn't write to it right now, which seems fine, right? But then when I put read-only, it definitely did say that the thing is not writable. So I don't understand why that thing, like why, okay. So this is a problem, I'm not sure if it's a bug. Let's, you know what, maybe we should, I wanted to try, let me try this briefly. So here's what I really want. So I kind of selfishly want to use a normal that's smaller for like this. You don't need a full float to store normal components. This is way faster because this is less memory. There is a more compact normal format that we'll start using probably soon, but this is good enough for now. And then I want to say, hey, just divide the components by 255. Well, I guess I want, what do I want? I want 0 to be exactly representable. So I want to subtract 127, and then I want to divide by 127, which I guess is equivalent to just doing this. This might not compile because, right. So the problem is GLSL doesn't support these types. However, there is a hope. The hope is, let's, hold on. Before we break the world, let's do another checkpoint commit. Vulkan AMD drivers on Linux, or at least RADV or RADV, or however you pronounce it, does support push descriptors. I don't think the desktop drivers support push descriptors. I don't think Linux, like AMD Pro or whatever the official AMD driver is called, I don't think that does. I think RADV does support it, so RADV might work. All right, so yeah, checkpoint commits, because we might break things beyond repair. So yeah, okay, like let's do this again. I want this. NW is just padding. We aren't going to be using this. So I want to do this. This just remaps from like 0 to 255 into a -1 range in a way that feels reasonable. So now GLSlang doesn't know what this type means. However, there's a GLSL extension. There's a Vulkan extension called something 8-bit. I forgot what it's called. VKKHR storage. Let's just, there's a list of extensions here somewhere. Yeah, VKKHR 16-bit storage and 8-bit storage. And there is a GLSL extension for each one that I forgot how it's called. This part of Vulkan is something that should have been better. Yeah, so there is an ext shader 16-bit storage. So let's do extension, I think it's like this. Maybe it's like this. Yeah. And Then the other thing is it's complaining about one other thing, and I don't know if this things even work in our driver. But in theory, right, if we use these three magical extensions, then we should be able to use uint 8 and uint 16t in like various places in our shader. To be able to use these, we need to enable, I think, this extension. This is a device extension, so we'll just add 16-bit storage. It's probably like this and like this. I don't know if we need this one. Oops, explicit what? Arithmetic. Probably not. Yeah, so maybe this is good enough. And then when we create our vertex data, we need to hope I'm not getting a cold. I don't want to deal with rounding right now. This is not quite the correct way to do this, but man, I'm definitely getting cold. Yeah. Haven't we passed an extension? Okay. So NVIDIA drivers handle this perfectly fine. There's a problem. I thought we are passing the extension. Let's read the extension text. Maybe we have to enable it. Oh yeah, storage buffer 8-bit access. We might need to enable it here. Is that true? Well, not here. Yeah. All right. So, right. Yeah. So the validation layers are perfectly correct. We are not requesting explicitly the enablement of the thing, which is great because somebody was asking what are these pnext pointers for. So here's what's happening. We are enabling an extension that that we want to use to be able to use 8-bit types in the shader so that our vertex structure is smaller. To request this, we need to say, hey, I want this extension to be, I want like to use the 8-bit values explicitly. And let's just do 16-bit as well. Features 8. And for now we only need... For now we only need storage buffer. So let's just do only storage buffer for now. And let's do the same thing for 16. Alright. Oops. Wait. Oh, 16-bit is now in Vulkan 1.1, but 8-bit is not yet, so probably it will be in Vulkan 1.2 or something like that. All right. Yeah. So we have to pass these guys to the device. And probably the way it works, and it depends a bit, it's like various extension to extension. Normally this features struct would have a next pointer, but it clearly doesn't, unless there's like a features to or something like this, but I don't think so. Oh yeah, okay, there's a features to. How are you supposed to use this guy? Oh, this is get physical device features. Yeah. Okay. Yeah, so let's switch to this guy. And so the way it's supposed to work is that you specify the struct, and you specify like we want to pass these 3 structs to this API that technically doesn't know about any of the structs. And so the way we'll do this is by creating a linked list, essentially, where create info has a pnext pointer that will point to features. Features has a pnext pointer that will point to features 8, and features, well, we should probably do it like this, because this thing is core now. Doesn't really matter really, but yeah, and then features 16 is features 8, and so in theory now should I enable more than just storage buffer? No. So we're still getting a validation error. But this probably works, because if we don't enable this, then no. Oh. What? I don't really understand what's happening anymore. We aren't getting the other validation error that we were getting before. Maybe this validation error is the first one and it subsumes that, okay. This is weird. Int 8 is a bad. Let's try to do it like this. Yeah, so SPV capability int 8 isn't present in the source for any layers. Maybe validation layers don't support this thing yet, so it doesn't work. Is that possible? Let's try to do in 16. You know what, let's let's look at this source. Shader validations PH should be here, right? Yeah. So we are calling SPV validate. Oh, it's not. I see, the source is not here, right? Yeah, it's here, I think. All right. So now let's do the search again. Validate capability. Right. Okay, how does it handle in 16? Is support optional? So it's creating an environment, and then it's passing this module, and then I don't see anywhere where it passes any information about any extensions that are present. I think what might be going on is that we might be passing, our shader requires 8-bit types. The validator says that the thing requires an extension. We are providing an extension. I feel like maybe what the problem is that the validation layers don't provide the extensions as an input to the validator. So there's this operand desk, num extensions, SPV. Validation has any of extensions. Oh boy. Module extensions. No, that's right. Yeah, okay, I don't know. It might be that we are doing this wrong, but it might be that I don't even understand how it tracks which extension enables this right now. There are tests for this. Alright, you know what? We are in a weird spot where we have a validation error. So if we check in the code, we get validation that's broken. However, it might be that we are hitting a bug. So that's not quite clear to me. But it might be that we are doing something wrong. And I don't quite understand right now what the problem is. So that's slightly unfortunate. And also this read-only buffer thing was really sketchy, right? So I think, like, right now it doesn't show up, but I think it's just because... so let's stash this thing. Oh, I installed a NuGet. The NuGet beta has a built-in stash that doesn't go through like bash in Windows, and it's so much faster. It's making my life so much nicer. So yeah, oh, we aren't getting the read-only problem anymore. Oh, right, yeah, because we are working, sorry. Oof. This is because we are working around this. So, like, this also doesn't really make sense to me. Because why would it be a read-only thing? Why is has writable descriptor true? Right? Like, I just don't understand this. I mean, maybe it's correct. I just don't, like, I'm not... I haven't, like, used this feature before, so I don't feel like I'm in a position to say there's a bug, because I don't have experience with this. But this is suspicious, because why would... Let's just, you know what, let me just debug this. So, var non-writable. I want to spend like a couple of minutes debugging this, and then I don't know. So we have an ID is 14. So okay, so let's take a step back. So 8-bit stuff works. The problem is 8-bit stuff triggers a validation error. I am not sure if it's a validation error that's legit, like we are doing things wrong. It's like we forgot to pass some extension somewhere, I just don't understand. Or if there's a bug. It might be a bug because on cursory expansion, inspection, I haven't seen a place in the validation code that looks at the extensions that we have enabled in the device. However, I might have just missed it, right? So maybe it's just a bug on our end. This thing is the same category where it might be a bug on our end, where, I mean, like, we have said read only in the shader, but maybe it's not in the right place in the shader to set it, right? Or it might be a bug on validation layers, because, you know, like, the coverage of all of this stuff is not always really good. Like, there could be a bug here, nobody has hit it before, because people who have hit it just didn't report it, or people just set features to all features available on the device, regardless of whether they need it, and, you know, just miss them. So let's leave the 8-bit stuff for the next stream, or maybe I'll look at the 8-bit stuff offline and report it. Well, that would not be in the spirit of the stream. I'll think about this. But yeah, okay, so let's just, like, I want to understand this problem. I want to understand at least one of these problems. I don't understand any one of these problems. So here's the deal. So we have somewhere here, it would probably be useful to do a text dump. So we have our vertices structure. That is... Oh, wait, this is not good. I want a row ID. All right. Oh. Interesting. We are decorating something else with read-only. We are decorating the... Well, Jealous Lang is decorating the vertices. No. It's decorating the struct. Oh my god. What? What? Where should read only be? Whoa. 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 Damn it. Yeah, that will be like impossible to figure out like this. Let's look at some examples, shall we? Right? Isn't this what we are doing? They have a name. We don't have a name, but that shouldn't matter, should it? I think now I have to say the name. Yeah, so now I have to be like this, right? Yeah, so we just named the thing that was the problem now. So the problem is that we are decorating like, man, it's even worse. So the thing that has a binding, so like our shader parameter that's a buffer is the internal ID in sphere V number 14. It has a descriptor set, it has a binding. There is a different thing, which is number 12, which is the buffer block. But it's not even decorated with read-only. Its member is decorated with read-only, like the vertices struct. What happens if I have an int here? Does it decorate both of them? Yeah. Okay, so the members of the struct, not of the vertex struct, the members of like this sort of implicitly declared struct are decorated as read-only. However, it's contained in, come on. It's contained in this other thing, which is a buffer block. And there is no read-only declaration here, which I don't know why happens. I'm assuming there's no real difference between these two. Yeah, okay, this didn't change, which is good. Oh, wait, let me remove this now. So I feel like what might be missing is something like this. Okay? Maybe. I don't know if this is true. How is this guy linked with... Oh no, what? Maybe I'm wrong. No, maybe I'm wrong. Maybe the thing that's missing is like this. But I don't know if non-writable is like a... Oh, this, sorry. Wait, what? Alright. Yeah, okay, I don't even know. Let's look at what this does. Really? Oh, okay, no, that's different. Yeah, so when we see a non-writable decoration, yeah, so I don't know, something really sketchy is going on here. I'm pretty sure our code, at this point, I'm reasonably sure our code is correct and like validation is just broken here. But I will need to read this PRV spec to say what part of this thing is broken. Like where the problem is and stuff like that. Similarly, in our 8-bit example, like I feel like we are doing things correctly. And it's really suspicious that, so when PRV validation layer does validation, it creates context from, it picks an environment, which is Vulkan 1.1. And what should happen is it should add the extensions to this environment that we have enabled. But I don't see this because the only thing that looks at extension is this thing that says if there's keychar relaxed block layout, it sets relaxed block layout. It doesn't set anything else. So I feel like what the problem is that this code, this code should be calling functions like this to tell something, maybe not like this. Let's see. Yeah, I don't know where this should happen. The other thing that might be happening is that we might not be enabling some GLSL extension. But it's weird that, no, this looks like it's not looking at, this looks like it's not looking at the extensions that are enabled on device. There was this, I'm surprised there's nothing about extensions here. But alright, I'm kind of tired of dealing with this thing. Let's just, so I'll submit everything up until int 8. We have one workaround for what I right now think is an issue in this PRV validator, where it doesn't classify our very much read-only, as far as I can tell, storage buffer as read-only. And PRV spec is really complicated in how and where the attributes are applied. So there's like layers of nesting there. There's like this 14 thing that refers to 12, and 12 doesn't even have the attribute, it has it on the member. So it's kind of nuts. I would not be surprised if there's bugs around this. Similarly for this int 8 thing, it seems sketchy that nothing is like enabling this capability in the validator in this code. And if this is the case, then this code is just buggy and we'll need to file a bug. So I think best case, we are just missing something really obvious to people who have worked with this before. This is my first time writing an int 8 in the shader. You can see it worked fine in the driver. It doesn't work fine with validation. So worst case, so best case, we don't understand what's happening in both of these. Worst case, we have found 2 bugs in our first use of this feature in the validation stack, which I think is what's happening here. But we will see. So I might research this a bit offline and file some validation bugs and figure out how we wanna like work around them. Maybe we just say that we know there's a broken validation, so we just don't. Like maybe what we will do, what our debug callback allows us to do, is to say, hey, if like the message contains this bit, which is like the best way how to ignore this, then we'll just return vk false. And then, you know, there's still a validation error, but it's like silenced, right? because this is like broken. This would be a workaround. And the same thing for these image stores. So actually maybe let's do this. So that it doesn't feel like we've done all of this work for nothing. Stores. Let's disable this thing. Oh. Now that is not even a problem. Oh, that's because there's only one message out of validator that can happen at a single point in time. This thing is just broken, so I'm assuming that, like, right now let's make a pessimistic assumption or an optimistic assumption depending on what you value more, Vulkan layers quality or our code. That our code is correct. We will investigate this later. It's not clear if this is a bug in our code or in validation layers, but it sure looks like a bug in validation layers. And also, there is a kind of another thing. This error seems to be masking another error, where validation layers seem to think that our vertex shader uses a writable descriptor and wants us to enable a feature we aren't using, which also seems like a bug. So yeah, given that both of these come from exact... Oh, is that true? No, yeah, actually maybe this isn't masking. This other thing was from a different call stack. It was from pipeline creation. So I don't know, maybe this isn't masking this, maybe it's not. Maybe there's some other problem. I don't know what happens. It's kind of suspicious. But the good news is our code works, at least on an NVIDIA driver, right? I might try this on an Intel driver on my Surface Pro later, just as a second data point. But really, the fact that something is wrong here, it's like weird that this other error went away actually. So, like, it's weird that the floating point code actually hits in a very different call stack when we create the graphics pipelines. It's very weird that we aren't getting the exact same problem, which should be the case. So, okay, yeah, maybe we won't submit this code because I want to investigate both of these. Both of these feel like bugs in validation layers. All right. So it's been like 2.5 hours. We have got a mesh on stream. We have used two new, not sort of new, but two things in Vulkan that seem like the future. One is not using fixed function input assembly interface and just binding the buffer to the shader. The other one is 8-bit types in the shader. We have hit issues in validation with both of those, which is not encouraging. But the code works on NVIDIA drivers, which is encouraging. So that's good. We will look at, we'll clean up the 8-bit stuff and look at some performance metrics and some other things like this next time, and maybe start sort of fleshing out the... Oh yeah, the other thing that we need to do is we need a depth buffer, which we don't have right now. So we'll do some stuff that kind of moves us closer to having an actual renderer with a 3D camera with a depth buffer and all of that next time, and also take a look at some of this validation stuff, which we seem to be hitting for no apparent reason. So that's that. If anybody has questions, I'm happy to answer them in the next like 5 minutes or so, and then we'll end the stream. And the good news is the driver worked perfectly fine with everything, right? The bad news is we again have hit two validation issues that we don't have a clue about, that might be bugs that we'll have to investigate. This is a problem. We have hit a bug in validation layers, a crash in validation layers on our first stream. We also have hit an Intel driver bug that was kind of minor, like on the second stream. Haven't hit any bugs on the third stream, I don't think so. But today we have hit 2 bugs, right, in validation layers. So after the first 2 streams, I said that we are averaging 1 bug in the Vulkan software stack as stream, and this is still, unless these 2 issues are our fault, or one of them is, which I don't know if is the case, but if these are both not our fault, then we are still averaging 1 as stream, which, you know, the 1 bug per 2 hours. Alright, so yeah, there's nothing, there's no questions on chat, except for how long would it take to make a really spaghetti version of Minesweeper. I don't know. I have never written Minesweeper. We're not going to be writing Minesweeper. Why do you need the Minesweeper if you have this? Well, why do you need the Minesweeper if you have a validation error? But also, let me double check that. Alright, that's fine. But also, why do you need a Minesweeper if you have a beautiful kitten on screen? It's slightly spotty kitten, but you know, we love the kitten nonetheless. Oh, and I guess we'll have to fix that. Yeah. When you resize a window to be 0 on one of the axes, validation layers complain. We should not be doing a resize in this case. Alright. Thank you for being on the stream. This was slightly painful because, you know, we used features that are poorly documented, poorly... Like the fact that you have to specify... No, this one is good. The fact that you have to specify like these 3 extensions in the shader and the Vulkan spec doesn't seem to refer to them at all. Maybe I missed it. X shader 8, right? Like there is no X shader 8-bit storage extension in the spec because it's a GLSL extension. But you kind of have to use this guy, and also you have to use the C++ extension, I think. Like the storage 8-bit. Alright. I will fix my editor setup is weird, so I'm constantly doing things that worked in my old environment. This is because this computer has been set up basically last night, so I didn't have time to do things properly. Oh, it's not even in this. Okay, never mind. Yeah, so we're enabling like 8-bit and 16-bit storage extensions. Oh, 16-bit storage might be Vulkan 1.1 thing, by the way. Yeah, okay, we don't really need this guy because we are using Vulkan 1.1, but we do need the 8-bit extension because this is not in 1.1. Anyway, alright, yeah, so that's it. That's the stream. We have rendered a kitten. The kitten was nice. Could it be some perf penalty because of using push descriptors compared to regular descriptor sets? It depends on the architecture. On NVIDIA, I have done some measurements on this a year ago, and push descriptors were faster for textures. Yeah. In Roblox, our Vulkan renderer uses 3 descriptor sets, 2 descriptor sets. Yeah, 2 sets, 1 for textures, 3 sets. Damn it, did we switch to... Let's just call it 2 sets, 1 for textures and 1 for buffers. And buffers mostly don't require descriptor set updates because they use dynamic descriptors, but textures do. And on NVIDIA, I tried this a year ago, and push descriptors were the fastest method on the CPU side. On the GPU side, it shouldn't matter much, but yeah, it depends on the architecture. On NVIDIA, push descriptors were the fastest way to do this. For small numbers of descriptors, right? If you have, there's a limit of 32. If you need like 200 textures or 400 textures or 4,000 textures, then you cannot use them. We will be using bindless extensions later in the series of streams, where we will have to use descriptor sets, probably, because we'll want to do something like, here's all of the textures in this level in one giant array. So yeah, but yes, on NVIDIA, push descriptors are the fastest way. I haven't benchmarked this on Intel. I should. Intel drivers had a bug with push descriptors that they have fixed since, so I should be able to do that. For our case, for now, it doesn't really matter. When will we be touching mesh shaders next stream? Definitely not next stream for mesh shaders. This might be, well, like we could technically, right? Nothing is stopping us. Except that it will be even more painful because it's like super fresh. The Vulkan SDK that I have right now is the Vulkan SDK that came out 2 days ago, and it's the first SDK that supports mesh shaders. So that'll be rough, right? Like the stuff that I was doing right now, we have hit 2 bugs, maybe, allegedly. We don't know. But if these are bugs, then one of them has been in Vulkan since 1.0, and one has been in Vulkan since the introduction of the 8-bit extension, which is not that recent, I don't think. Half a year? So mesh shaders might be really rough. I do like the idea of experimenting with mesh shaders, and I do want to do this. I just don't know if we are quite ready yet. I feel like next week we will be, we'll add depth buffer, we'll like add a camera or something, and then clean up some of the stuff that we have written on streams before. I feel like we might not be doing hardcore stuff next weekend. But yeah, maybe mesh shaders the weekend after that. That might be cool. Alright. Is there a best practices guide for the different architectures? No. There are some vendors that post performance guidelines for Vulkan. AMD has a lot of presentations, like there's a Vulkan Fast Paths presentation on GDC something, GDC 2016, and I think there has been a follow-up in GDC 2018 this year. And this tells you how Vulkan concepts map to AMD's GCN architecture, and what you should be doing and what you should not be doing. And it says there is a specific fast path that this outlines, where like you stuff everything in one giant descriptor set. We will be using something like this later on stream. This is a good idea. This is like a long-term a good idea anyway, even if some architectures right now don't work very well with this. Let me try to see if there is a... I think this had... Oh. Great. I don't have a PowerPoint installed here. Yeah, so there is good guidelines for AMD. And then there is, for example, ARM has performance guidelines somewhere. They have this PerfDoc thing, which is a good software layer, but also they had a PDF somewhere. I don't remember where it is. But there is like a good PDF from ARM on what works well with their... I think it's this one potentially. Yeah, so this is a really good guide from ARM. Oh, the link is now okay. But yeah, just ARM Vulkan Performance PDF. NVIDIA doesn't really have a really good comprehensive guide that I remember. But yes, different vendors have different, like, varying amounts of information. I think Intel had some reasonably good doc. But I don't know if there is like if you were to ask Intel Vulkan push descriptors, are they a good thing for performance? Then you wouldn't get an answer to this, right? The only really way is to benchmark. I think this might be an NVIDIA. Oh no, this is. Oh, this is interesting. Have I read this? Oh yeah, I think I've read this. This is kind of early. It's not clear how well it maps to all architectures. And this I think is from Linux Experience. Anyway, but there's no centralized resource where it's like, hey, use this thing on AMD, use this thing on NVIDIA, use this thing on Intel, which is unfortunate. Do you know any other good minimal Vulkan example applications which use Vulkan efficiently, transfer queues, trading, and from which you can learn? Yeah, I don't know. I mean, Sasha Willems examples are the like go-to sort of thing when it comes to Vulkan examples. They definitely, well, I don't know if Sasha uses transfer queues. There's definitely examples in his set that use device local memory, which we didn't do today. And there's some stuff that uses threading, but I don't really know how performance conscious these are, I guess, right? So I don't really know. The way I learned all of that is you read the spec and then you read all of these papers from various vendors and various people who have ported to Vulkan. Like, so this is high performance Vulkan from John McDonald from Valve, right? So this is whatever Valve has learned when porting to Vulkan in 2016, which is 2 years ago, which might be only relevant for the Linux drivers, I'm guessing, that they have ran this on. But it's a good set of information to sort of internalize. And yes, and then you just experiment. A lot of stuff you just have to write code in different ways and then benchmark it on the target architectures that you care about and then figure it out. All right, yeah. So thank you guys for being on the stream. It was a bit longer this time because we hit a bunch of validation snafu again. Streams continue next week, and as usually, for now, it's like Saturday, Sunday, 10 a.m. Pacific. All right, let us end the stream.